The planet from Interstellar fascinated me when I saw it in the cinema. 1 hour passing on its surface equates to 7 years on Earth. And then there are these enormous waves threatening the crew, all this while the planet orbits a gigantic black hole instead of a star. The mission to Miller's planet is one of the most thrilling and scientifically intriguing scenes in Interstellar. Could such a planet actually exist? Interstellar is renowned for its scientific accuracy, thanks in large part to Christopher Nolan's high-profile consultant, the physicist and Nobel laureate Kip Thorne. His task was to create the most realistic scenario for Interstellar's storyline, and Kip Thorne approached it with such care that he even published 2 scientific papers on unprecedented simulations of a wormhole and a black hole. The criteria for Miller's planet: it should potentially be habitable, with giant waves sweeping across it every hour, but most importantly, time should pass on the planet 60,000 times slower than on Earth. And, spoiler alert, all 3 of these aspects could potentially exist in our universe. But for that to happen, both the planet and the black hole it orbits would need to have very specific characteristics. Miller's planet is a mission destination because it could potentially be habitable. This rocky planet is roughly Earth-sized, with gravity only 30% stronger than Earth's. Moreover, it boasts liquid water, and quite a lot of it. Water isn't rare in the universe, but it's usually found as ice or gas, rarely in liquid form. However, Miller's planet isn't orbiting a star. It's orbiting a black hole that devours light. Shouldn't it be cold and dark there? Actually, that's not the case because Miller's planet resides between the black hole and its accretion disk, which is a hot disk of matter that accumulates around the black hole, somewhat like Saturn's rings. Magnetic fields in this accretion disk convert gravitational energy into heat and then light. Accretion disks around black holes can get as hot as 100 million degrees, emitting massive radiation. So, it's not too cold, but actually quite hot. Therefore, Kip Thorne tamed Gargantua, the name of the black hole near Miller's planet, and its accretion disk reaches only a few thousand degrees, approximately the temperature of the Sun's surface. Because Gargantua hasn't consumed a star for the last 10 million years, as determined by Thorne, which is fortunate, as the crew needs to walk on the planet without being fried. So, Miller's planet is warm enough to prevent water from freezing, but not so hot that humans would perish. Furthermore, the planet's gravity is strong enough to possess an atmosphere whose pressure keeps water in a liquid state without it immediately vaporizing. The gravity that the crew experiences on Miller's planet has nothing to do with the black hole, but rather with its own mass. When standing on the planet's surface, one experiences only the planet's 1.3 times Earth's gravity. The black hole doesn't make the crew heavier, but it's the tidal forces that create gigantic tsunamis almost hourly that are responsible, courtesy of Gargantua. Tides on Earth occur because the Moon's gravity pulls on it. This causes the Earth to be stretched along one axis and compressed along the axis perpendicular to it. Near where the Moon and Earth are closest, and on the opposite side, there are water bulges due to this. This results in high and low tides. The tides on Miller's planet, however, should be extreme. That's why Kip Thorne set Gargantua's mass to be larger, equivalent to 100 million solar masses. If it were even larger, the forces acting on different parts of Miller's planet wouldn't differ enough to create massive floods. If it were smaller, the forces would differ so much that they'd tear the planet apart. Thus, the planet is stretched into an oval shape, but it remains in one piece due to tidal forces at the tearing point. But this creates a new problem. If Miller's planet were to rotate like Earth, it would constantly face a different side towards the black hole, and the planet would be massively kneaded with each orbit, becoming a molten ball. This wouldn't fit the story, so Miller's planet rotates nearly exactly once per orbit, so the same side always faces the black hole. However, the alignment is not perfect. Miller's planet switches between 2 orientations every hour, creating the gigantic tsunamis racing across its surface. The reason Miller's planet is subjected to such significant tidal forces is its extremely low orbit. This low orbit is necessary for time dilation to work, and that's probably why you clicked on this video. A black hole has so much mass that it significantly warps spacetime. We can observe similar effects on a smaller scale here on Earth. The distance a radio signal has to traverse is 50 kilometers longer when it passes close to the Sun because the Sun warps space, and Earth's gravity is sufficient to slow time on Earth by 40 microseconds per day, compared to 20,000 kilometers above the Earth's surface. We can witness such effects on a much grander scale near the event horizon. The event horizon is the distance from the black hole at which gravity becomes so immense that even light falls into it. Within the event horizon, space-time effects are even more significant, but unfortunately, we cannot observe them. At Gargantua, the event horizon's radius is roughly 150 million kilometers, which precisely matches the distance between Earth and the Sun. To achieve the desired 60,000-fold time dilation on Miller's planet, an orbit must be as close to the event horizon as possible. To accomplish that, Miller's planet needs to rotate extremely quickly. I understand that might not be immediately clear, so allow me to explain briefly. For Miller's planet to find a stable orbit close to the event horizon, the extreme gravity needs to be balanced by an extreme centrifugal force, which can only be achieved if Miller's planet moves extremely fast. So how do we accelerate the planet? When a black hole rotates, it creates a space-time vortex that drags along matter. Thus, if the black hole's spin or rotation speed is high enough, it will also accelerate our planet. How fast does Gargantua need to rotate? Extremely fast, even for a black hole. The maximum possible spin for a black hole is reached when the matter dragged along reaches the speed of light at the event horizon. Kip Thorne calculated that at 99.8% of this theoretical maximum speed, braking effects become so strong that it becomes unlikely for a black hole to rotate even faster. Observations often show much slower spins. However, even the 99.8% isn't enough for us. That's why Gargantua is an exception. Its spin comes close to the maximum speed, accelerating Miller's planet massively. It orbits Gargantua in 1.7 hours on an orbit just far enough from the event horizon to avoid falling in. It covers the same distance as Earth's orbit around the Sun, about 1 billion kilometers. This rapid movement means that Miller's planet moves at almost half the speed of light, causing the extreme time dilation. So, on Earth, 7 years pass while only 1 hour elapses on Miller's planet. Thank you, Einstein. In conclusion, Kip Thorne constructed a fascinating world with Miller's planet, adhering to the boundaries of physics. Miller's planet is not impossible, but rather improbable. In the vast universe, the most unlikely phenomena can occur given enough time. So, as always, stay curious.